use Phyton to understand the process control. Okay, so before, okay, right. So we have planned to have one workshop end of this year in August. Okay, all right. We have planned one workshop on Phyton and data science in process engineering. So it's collaboration with UMP. The workshop will be at the physical workshop at the University Malaysia Pahang Gambang. Right. Detail will be you can contact Dr. Riza for more details, and the details will be published in our MyPCS Facebook. All right. So today I would like to talk. This is the content of the presentation today. So first, before we start, because Phyton is open source programming, I think from earlier Dini and Nazri did the introduction on Phyton. Okay, and now we have Phyton 3 and many version, and the update is rapidly. So before we do start doing the Phyton programming, it is better or is wise to check the system, so that some of the program or some of the library may be obsolete or maybe not relevant at a certain point, right? So and then after that, I will go a bit on the introduction to Phyton. I will just use one slide for that, and then I will mostly I will talk about the Phyton in process control engineering. This one I basically maybe for undergraduate level, and then after that maybe if you like or need keen to know more about how you can incorporate Phyton in your research, then we can do more collaborate or more discussion. Yeah. Okay, this is just to give you some basic idea. So how we can use basically during the undergraduate, we understand or we study about the Laplace transformation, and then we move towards the modeling part for dynamics, and then we end with the control system where we design the controller. Right. So basically, this is what my main focus for this evening. Okay. Right. For system check is this is my setup. So maybe it's different with your setup. So I have Phyton version 3.8. I'm using a Conda as my IDE. So whenever I want to do the coding or programming, so I use a Conda environment, Spider environment. All right. Okay, and then Spider is 4.2, and then my setup for my laptop is as stated there. Okay, maybe it's different with yours. Okay, all right. So let's say uh, if you have Spider in your system, if you want to know which package you are at, you can just use a Conda. So then you type Conda and then space list. Then you will list all the package that are available in your system, right? So let's say if you want to know the specific library, for example, in this case, for today, I will use more on NumPy, SciFi, and Matplotlib. So only these three main module that I will talk for today. So let's say if you want to know your version, right, then you can just type a Conda list, and then you can just type your specific package that you want to know. Right. Introduction a bit on the Phyton. Okay, Phyton is mostly it's just like normal. It's just like other programming language, and most recent, which is object-oriented programming. So it's about programming and expression. And then another one is a variable and assignment. So meaning that you need to think of how you create an object in the programming, and then how you combine the object to form a expression. For example, x equals to 1. Those are the object x. Then the expression is equals to 1. So meaning that the value that you bind with the object. All right, and then after that, take a variables and a name, right? Okay, so I must state it here. Programming is not the uh, programming is in programming uh, we don't solve for x. For example, like this. If I can write the whiteboard. Okay, can I not? Okay, so for example, x equals to 1. So this is expression. So this statement meaning that y equals to x plus 1. So y equals to 3. Then you ask the program to run the code. Let's say this is your code, y equals to x plus 1. Right, so this is programming will not do like this. So if you want to ask or if you want to do a programming, I think most of you know all this. Just you need to rearrange the formulation so that you manipulate the object of y and then you bring it here. Then you need to have x. You need to solve yourself unless you do some. Uh, this is minus, so this is plus 1, right? Something like this. So meaning that you need to rearrange yourself. This is a simple code to solve x, unless you do some model to some package to solve, like you use uh, what they call root finding methods or others numerical methods. Yeah. So this is important so that when you write a code, so don't write. I mean, y equals to x plus 1. So the computer will not find x for you. So you need to find x for yourself. All right. So this cloud basically is just like you store the value and inside the computer, and then computer hold the value temporary unless you write in the file or in the physical file. Yeah. Then it can store permanently. So in this case, for example, the cloud represent the temporary data, temporary storage, so that when you assign pi, in this case, this is number, and then you assign radius into the 2.2, and then when you assign again radius 3.2, meaning that it will override the first one. It's just like that. So this is object oriented. So this is the object, and then this is the value. The arrangement is the expression. Yeah. Okay. Right. So for today, so that's just the introduction, and then as we go on, I will talk more a bit on the how Phyton, how the syntax in Phyton will look like. Okay. All right. So a Laplace transformation with Phyton. So basically, I will use SymPy. So this is symbol approach. So meaning that you convert the expression of x, for example, uh, not good. So let's say we use g equals to a plus b. So this is g a b is assigned, but is you will assign this object as a symbol, right? So it's just like this: 1 negative e. This is the in the time domain, and then 1 over s. This is the s domain. So later we will convert the value of t as in term of a symbol. All right, and then the tau maybe is a number, yeah, number, a constant. All right, so we use sim, sim, symbol Phyton. So in this case, there's many in this package. So this one we call module or package. Yeah. All right. So I just focus on the Laplace, but there's many more basically you can run this. You can use this SymPy for the mathematical expression or mathematical needs. Okay, so in this case, I will just focus on the Laplace for a transformation. We use this function, library transform, and then another one is the inverse Laplace transform. Okay, so basically, we have a time domain. We want to translate or we want to transform to a Laplace domain or vice versa. Right. Okay. So for example, number one, we have basically when we want to run a Phyton, if you are not, if you want to use other people library, so this is other people library lah, other people module or package. Yeah. So we need to import this package, and then you assign into any name, so any object. All right, so in this case, this is not necessary, but if you have a long name for your package, then it's wise to make it short. Yeah, so either you can just py directly here, or you assign to a object, so that you can manipulate this package. Right, in this case, I will just use SYM, and then I want to assign a symbol that I want to use for this case. So T, S, and A, this is a symbol that I will use for this example. And then this is just a setting to let the system knows, to let the Phyton knows that the number that I'm operating is all a positive and true and real. Yeah, positive and real, more than 0 and R. Okay. All right. So another one is once we assign this as our object, a symbol, right? And then we need to write in the expression. So this is the expression that we have, a symbol expression. Yeah, this is different with y equals to ex negative a times t. So if you don't apply this, you don't assign a and t as a symbol, then you can just directly use in the normal mathematical operation. Yeah, but in this case, I will use a symbol base. Then I need to have a symbol, then dot exp. So this is the object inside this package, and then this is just a definition of this. Yeah, definition of this equation. So basically in time domain, I want to have this as the function for the time domain expression. Now the purpose is to Laplace this, then I will, then at the end I will get this information 1 over s in bracket. So what I will do, so this is a symbol, and then Laplace transform. So this how the Phyton call the system. So it's just like a dot, and then you call the function inside the package. Then this is a function Laplace transform, right? And then for here we add the information of a equation that we want to transform, and then this is T and S. All right, so this is the from, and then this is N. So from time domain, and then we want to translate to S domain, and then the non-condition is true, right? So it's true. Okay. All right, and then after that, basically, if you want to do the transformation, you just need to have this code. Yeah, so this code. So this is the key for the Laplace transformation, but it's not what I call it's not satisfied, or we think that we don't have we want to know the answers, right? So if you want to know the answers, it is in Phyton we use print. So meaning print, we will print in the console and console output, and then in this case sim you can print as a latex format. So this is a latex format if you want to have a latex format, or another one you can just print fs directly, then you get a normal line based equation, right? So if you look at this line, so I will print in the latex format f. So this is the expression, then I will get something like this. So, all right. So, and then another one, fs. So after the conversion, after the transformation of f, small f, and then I will get this as my second output. Right. So let's say if you want to see the how this will look like in normal formulation, normal form, or equation based form like this, then maybe you can just use this website. So you just type or copy paste the output from the Phyton, console, and then paste inside this website. Then you can have some similar something like this. And if you copy and paste this one, and you have something like this. Or if you have latex in your system, let's say when you write your thesis or your report, that latex is available, then you can just copy paste this inside your document. Then it will display the formula, nicely arranged formula like this, right? Okay, so this is one way. So Laplace of this function, and then another one is inverse Laplace of fs, right? So another way around, right? And then it's still same. So you need to know what is your function that you want to Laplace. So in this case, you have something like this. So in Phyton, for mathematical operation, we have multiplication. So we have divide, and then we have plus, we have minus. So for power, we have like this, right? So meaning that's 2 times 2. For example, in Phyton, we use 2 star 2. So divide 2 divide 2, then no, not like this. How to delete? Not like this. 2 divide by 2, then we use like this lah. Okay, and then 2 plus 2, 2 minus 2 is the same. And then 2 power, in this case 2 power 3, for example. Then in Phyton, we use 2 double star 3. Right, so let's say you want to have 1 over s square. In this case, it's a ramp function. So then you need to have, in this case, f s equals to 1 over s star 2, right? In this case, if you want to use ramp function. So in this case, it's just this is a first order system, first order function. Okay, and then I will write something like this. Right. So this is the function, or the Laplace function that we want to inverse. Still the same. So we use a sim, and then another one, the key for the inverse Laplace is this name, right? So this name. All right. So and then again, so the function that you need to put in here, and then from S you want to convert to T, right? So in this case, I don't put the none condition because I already specified in this case, right? So and then again to display the outcome. So basically what you get is the one like this, and basically it's just inverse from the one that we have from example number 1, right? Okay. Okay, so maybe another one. This is the sum of the Laplace transformation that available in this table. Maybe if after this, if you have time and you want to try yourself for the Phyton environment or Phyton programming. All right, so you can use you can have this function and then convert it to Laplace or inverse Laplace, right? Okay, so if you look here at this one, I changed a little bit on the calling function. So basically in Phyton, so we have example number 1. So in Phyton, basically this is small I. All right. So basically in Phyton, so the first of all you need to open with the calling the library if you have the library. So basically, my point of view is if you have a wheel, we don't want to reinvent the wheel, right? So we just apply the package that people have developed for us. All right. So basically, just this is the add library. And then second part, basically assign or declare or assign, and then operation. And then the last one is display output, right? Basically the operation, or to write a program in I think in most of engineering or most of programming language, this is basically the arrangement is look like this. And not for example MATLAB we don't have the add library lah. add library. But if you have C, then you need to have a library or right. So depends on the environment that you use. Okay. So for Phyton, basically you need to add a library, what library you want to use, and then declare accordingly, and then do the operation. Once you've done the operation, you did the print. Either you print the text basis, it is a text basis, or you print in terms of a graph or in terms of table. Yeah. Okay. All right. So in this case, I make a little bit different. So basically, earlier I will use import sci symbol pi, right, as symbol. So basically it's like this. If you apply this one, then you can add all the package that available inside the SymPy. Right, but in this case, I know what I want to use. So in this case, I'm using symbol, I'm using Laplace transform, I'm using inverse Laplace, so that I'm only call these features only. The remaining features in this sci-fi SymPy, I'm not using it. So meaning that I will use less resources for my computer. So you will not load all the available function in the SymPy. I will just load symbol function, Laplace transform and inverse Laplace transform. So this is depends on the some depends on your capacity of your computer. Yeah, but for this one it's a bit just targeted to the certain function. Right. So in this case, if I use like this from some symbol pi, sympy, import symbol. So meaning that I don't need to put sym in the beginning. So if you look here, so I will not need to include this. But both way is fine, not a problem to in a programming wise. Okay. And then another one, there's a very good features in Phyton is a definition. So definition is a declaring a function. So it's just like in any, it's just like if, for example, in MATLAB or in C or in VB or others. So this is a instant function, instantaneous function. Yeah, instantaneous function where we declare this as a function. So in specifically for Python, so the format to declare function is this is the fixed format. So you need to have define def space, and then this is your function name, and then depends on you want to put a argument or you don't want to put argument. So this is optional, and then you need to have a double dot here, right? And then another one is what they call this one, uh, indentation, indent. So indent must have, you need to have indent to, so that you make a block, a sub block inside the function. So meaning that indent, and then you need to put a return, or right, return or not return also. It depends on your output lah. So if you want to have output, then you put return. If not, then whatever inside after the indent, this is called inside the block, I mean inside the subsystem. All right, and then if you want to write again for outside, I mean for you need to proceed for the next statement or next function, then you can unindent back, and then you start at the same direction, right? So this is in Phyton. This is the unique in Phyton. So they don't have, like say for, let's say for C, we have a curly bracket to make sure that this is inside the block of your subsystem code, or in MATLAB, for example, you have function and then you need to put n, so that all inside the block. But in Python, you need to have a indentation like this, right? Okay, that's why I'll put like this. And then if you look here, I'm not using the Laplace transform. I will just as Laplace, meaning that I will just assign this function as an object of Laplace, so that I can manipulate Laplace names here. And then I will, the rest is the same like the one. So argument here, f means the one that I want to pass through the function. Right, this is the system lah. The okay. Right, and then another one is a repetition of the first one, and then this is the same. In this case, it's inverse Laplace, as according to the name that I showed here. And then once you declare these three, I mean, when you put these three at the top of your program, then you can just manipulate. You can just assign or call, invoke this function. For example, you want to do the inverse Laplace, then you need to prepare what is the uh, Laplace equation for your case. So in this case, I will use 2 over AS, sorry, not AS, 2 over A plus S square, right? Okay. So in this case, let's say I'm using this one as a test, and then f is a small in the time domain, inverse this function I will put it here, and then print this one. So this one is print without the latex format. I just print this information, then I will get something like this, right? So when we check the system, and then we get something like this. Yeah. Okay, so basically it's a 2 in front, that's why you have 2 here basically. Yeah, so like this. Okay, so this is how we do Laplace and inverse Laplace. Okay, you can try this code at home at your time, and at the end of the presentation, I will share the code for you to try and check whether you get the idea or not. Because sometimes when you copy paste, sometimes the code, especially for code here, they will have some error, right? Unless you type it yourself. All right. So another one. Now, after Laplace, we move towards the process modeling, and this is the very basic, I think, water level model that most common to us. It's very good to visualize and understand. All right, not like concentration or temperature. So it's not visible, but if you have like a water level, I think it's much more easy to relate with the situation. Right. For example, let's say we have something like this. Basically, this is the ODE, and then how we translate to transfer function is basically we just use a Laplace transformation, and then we apply, and then I get something like this. Okay. So for this one. Okay, so this is a first order system, and then in the process modeling, at the end, we want to get the graph, something like this, where we want to understand what is the final value or process gain. Another one, we want to find the time constant, right? So this is the most important in the characterization of a first process, right? So in this case, I've prepared this code, and this is a simple basic code that able to get the graph, but I remove certain miscellaneous code just to make it beautiful. For example, the graph, just plot the graph, but it will not look like this. If you use this function or this syntax, you will just get the graph only, right? Okay, so for this exercise, I'm using NumPy, I'm using SciPy and Matplot library. All right. So if you look here, now I know what I want to use, which what I call which function in the package that I want to use. Then I will just do like this. If let's say you're not sure what package you want to use, then you can just use SciPy. You can use import, and then SciPy, import SciPy. Okay, and then another one is import NumPy, and then another one import Matplotlib, right? Import Mat. Okay, it's like this. So and then after that you need to let's say sci-fi as something, then you can just call this one lah as for example, then s dot signal like this. So need the calling is a different if you start with a different definition, yeah. But this is two way to do. So either you do from or either you do from import. Right. So this is the number that for my at the moment for my code. So this code is valid for this version. I'm not sure for old version this code still valid or not. Right. Okay. So for this transfer function. So for the first of all, I will discuss this part. So how we do the process modeling for if you have a transfer function, and then in the transfer function we assign something like this TF or transfer function, right? So it's just like earlier Laplace Laplace it looks like is Laplace transform, right? So like this. So Laplace inverse Laplace transform. So meaning that this is the function that you call. So in this case, I'm using transfer function. So because since this is this is a little bit lengthy, then I'm using just a TF to make it short. TF, and then this is the same like the one that we normally use, linear time invariance, LTI system. So numerator and denominator, then you get something like this. So for sci-fi signals, there's not only the transfer function. You can use a steady state, state space model. You can use a frequency model or many more. Right? So in this case, I will just give you a very basic idea. Let's say you have this information numerator and denominator. Then if you want to create a transfer function, in this case I call system, then I will just use a transfer function and then put it accordingly. So this is, if you hear this one is represent, I think most of us understand this information if you're very well versed in MATLAB. So this is something like this, right? So basically 2 is a coefficient of the numerator, and then 6 and 1 is a coefficient of a denominator in the polynomial base. Right. So and then after that you will try, you just want to understand if you have this transfer function, what the response would look like for input step, right? And then in this case I just use step. So why I can do this step, just because I'm assigned this and then I import step, then I don't need to do the calling, the lengthy calling. All right. So much more simple for my case. All right, but it's not flexible. Most of the programmers, they will just start with the signals dot step, so which is much more flexible to call a signal, so that they just call the first only, don't need to call many times. Right. Okay. In this case, step and then step the system, then you will get something like this, right? So just this is the one, and then in this case it's a blue color. So if you look here, there's a overlap of it. It's a Laplace in the blue color. So the code will be like line by line. So you evaluate this code like this, yeah. So if you look here, the green color, this is the comment, so that the compiler will not evaluate the comment line, yeah. Okay, so in this case I call this step, and then step will give output in term of t is a time x axis, and then y in term of y axis. So and then after that I will do the plotting. So the plotting here I'm using matplotlib. Okay, so this one is x axis is just like a common y, and then this is the features of the plotting, right? So this is just a very basic example how we can plot the response if you have a transfer function. So another one is ODE. If let's say this is mostly common, I mean, so let's say this is the model that we want to simulate, or we want to get the characteristic. So in this case, it's most, as I can say, that this is we can use these features or this approach for research purposes, where let's say we have a very specific equation ODE, then we can just plug in inside here either linear or non-linear, complex or non-complex. So it just if your model able to solve or is under the explicit form, so under the ordinary differential equation, then you can use this and you can extend this to a research level, right? And then this is the model just like the one A dh over dt equals to input minus output. Yeah, so output is in this case is 0.5 h. So A will put it in this side so that I can rearrange this one. All right, so this is the model that we have possible, just a very basic ODE. Right, and then once you define your model, so you need to solve the model. So solving the model, as I said, if you have the wheels, then we don't need to reinvent the wheels. If you want to reinvent the wheels, that's not a problem, because in research we can have many improvement, many limitation for certain numerical methods. Then in this case, this is just using a normal single Rangakata ODE integration. So or you can write your own Rangakata model or Newton model. Yeah. So in this case, I just use ODE integer. So this is in this case integrator. So I'm using ODE integrator. So then this is the model that I'm this is the model that I want to put in. I want to solve. All right, and then this is yes, because numerical differentiation or numerical integration, you need to start with the initial value, and then this is we put, let's say, 0. Right, 0, and then I put it 0. This is the initial value, h at time 0 equals to 0. This is the value here, and then this is, I want to know how long the simulation will be. So in this case, I'm using from 0 to 40, so meaning unit time, time from I want to simulate from 0 to 40. And then this is just numpy, so that this is just to create a linear space of a number from 0 to 40, which has a 50 member inside the interval. 50 number. Okay, like this. So this is 1. This is n. So you have how many in between? 1, 2, 3, 4. So you have 4 points in between. Yeah. All right. Okay, so just like this, and then after that is the same. The process is the same. Like the first one is add the library, and then define. Then you do the operation. Oh, sorry. So define. So this is the operation, and then this is display. Same, and then this is repeat again. Define, operation, display. Yeah. All right. So this again there's many way to put the library or the package here. You can put at this junction, or you can put at the top. So normally when I did the programming, I would like to make it all in one place, so that easy for me to add and check. Then normally I just put the top, but not necessary. Some they like to put at the inside the line also. Those also possible. Right. So if you look here, once we run the code for the ODE integrator, and then we have H, and then H will put it here, and then tsim is the one that our number or the value from 0 to 40. Then this is X value and this is Y value, and then I will plot according to R and double dot. Right? So this is the format for the plotting. So then I'll get something like this. Since the both process is the same process, then I will get the graph will overlap onto each other. All right. So this is a very basic understanding of process modeling. Once we know this, then it's easy and for us to develop a model and check whether we get the response that we look at. Yeah. Okay. And then another one, let's say we want to improve or you want to know, you have a little bit complexity, you add some another portion of tank, for example, another ODE. Let's say you have two ODE in series, then you want to solve this model, and then let's say at the end of the day, you want to know what is the response for H2, or if you want to know H1 also, it's still possible. It depends on what you want to see, right? So in this case, let's say, uh, all right, okay. So let's say in this case, I have second tank here. So first tank is remain as is, and then I add another tank, a little bit smaller, and then I would like to do the plot, and then I want to do the model. I want to see the character of the plant, of the process. Then in this case, it's the same. The repetition is the same. From here, I will translate to here. From here, I will translate to here. Right? So we'll get something like this. All right, and then okay, so still the same. Start with the definition. So in this case, I will use a little bit. I add this one, poly multiplication. All right, poly multiplication. So poly multiplication basically is a you want to multiply the system or the model transfer function. For example, we want to have something like this. So this is the first G1, and then we have a G2, something like this. So in this case, we have Q, we have H1, this is we have H2, right? So this is Q1, right? So we have a transfer function for the first one, this one, and then we want to have H1 over U1, and then we we have another one is uh, H2 over H1, right? And then we get the overall transfer function. Okay. So in this case, this is a multiplication approach. So that's why I'm applying this technique. So this is just a basic idea, rough idea on how you can do the multiplication. So as now there's a few programmers did the simplified version where they can just do like this. For example, multiply G1 comma G2, right? And then you get G. So this is many programmers did this multiplication. Just apply this and then get the idea, get the overall transfer function directly. But in this case, I would like to basically what they did is they just still use they take the information of first system, first transfer function, and then they get the numerator. All right, and then after that they multiply with the second transfer function. They get the numerator. Then basically it's a multiplication of the polynomial. This one is a polynomial multiplication. So meaning that it's just like this, the same like the numerator. Okay, again in the Phyton, especially in this case, this is basically is a one line segment. So because of I have limitation of the code, basically I'm not used like this, but this is one way to write the code in Python. So basically this is referring to this separated by comma, and then this one referring to this. Yeah, so only in Python that it is possible to use something like this, right? Okay, and then another one is a numerator and denominator. So in this case, since I know my system for transfer function 1 and transfer function 2, then I want to assign the numerator for combine. So then I will have something like this. And then the numerator for combine, I have something like this, right? And then from here, I can get the overall transfer function. So in this case, we'll talk about overall transfer function for the system. So this is the So meaning that the transfer function that we look at here now is a H2, and then this is Q. In this case, it's a Q1 or Q. All right. So in this is Q1 lah. Okay. Like this. So this is a transfer function. S Y S. Right. So this one. So and then again, it's repeat again. Then we will just step, and then we try and see what happen if we have a combined two system. Right. Right. We have a graph something like this. And then another one, let's say if you want to do in ODE, yeah, if you have in the ordinary differential equation. So the way how to develop or how to write a code is just like as a line by line, meaning that you need to assign the dHdt one for this one, and then second line will be dHdt for the second equation. It's just like the one that we have here in the problem statement. All right. So for definition, you need to use the same format like this. So basically, the most important, the compulsory agreement that you need to put inside the model. This one is you can rename as any name that you find it reasonable. Right, and then the first one that you want to integrate or you want to find is H. So meaning that this is the must have changing in Y. So this is changing in Y, and then followed by time. Right. So if you know that if you use MATLAB, they will start with T first. Then you will cover with the output that you want to differentiate. Right. So in this case, just H or any names, but the format is the same. So this is the first one that you need to we will need to change according time. Right. So this is T, and then this is Y. So this is X lah. Okay. X. Okay. So meaning that the format must be Y first, and then this is X. So this one is must or compulsory for the first one, and then the following line is the additional. So meaning that if you want to supply the information inside your process, then you can comma, then you add another object. So if you don't want to put here, then you need to remove this, then you get something like this. So then meaning that it's defined inside the model. Yeah, defined inside the model, then you can just get the output. So in this case, H1 and H2, since H is a referring to value, then it's just enough to put it like this. So this is known that H will give you two value, which is because of this information, right? Okay. So this is the idea for the first one. And then after that, it's the same again, like this one, the ODE and the lean space. So this is just to create a system. In this case, the difference is if you have two state parameter that you want to study, then this is 0 and 0. For example, H1 at time 0 equals to 0. H2 at time 0 equals to 0. Same like this lah. And then if you look here, this one is a Q. Earlier there's a Q here. Then the format to put it like this. Yeah. So this is the format to put the Q. So if let's say you have many Q, many input that you have, for example, you have a disturbance, right? For example, this is D, this is Q, right? For example, then you can just put like this, D, for example. And then here you can add 1, 1, for example, like this, yeah? So then you have two information supply inside this model. So in this case, just one. Right. So another one like this. If you look here, the array is like this. So meaning that we add all the information since H is two column arrangement. So two column arrangement meaning that the data H is if you want to represent in term of a table. So this is H. So this is H at 0. This is H at 1. So and then this is 1, 2, 3 in term of row. So that's why they have a double dot here, meaning represent all the row. and then column number 1. So in Phyton it start with 0. So since it start at 0, so 1 is a column number 2. So we want to call all this information, and then we will plot accordingly. And then if you look here, the plot is on the top of each other. Why? Because this is it's the same process. It's just a conversion from ODE to transfer function. Yeah, right. So this is how we do the model. So once this is the first step. After we pass this, meaning that then we can start understand the dynamic of the process. Then we can just try our own our own input step. For example, if we have a very custom input to supply to the process, then that's what we do in the dynamics in the next slide. Right, process dynamic. So again, I will just repeat the same model that we discussed earlier. So in this case, I'm focusing on time domain system. So all right, and then in this case, I will have something like this. So in this case, we have, for example, this is the definition of the process model. Okay, later I will show you the complete code that I'm using for this one. But the most, I will just point out the relevant code for us to carry out the process dynamic simulation. Yeah. So basically, we need to have a process. We need to know what is the input that we apply in this process. So in this case, I have a step input where the step time at 5, for example. Then this is the way how we create the unit step. Yeah, this is how we create a unit step from 0 to 5, and then unit value from 0 to 1. Okay, like this. So this is the code for that. So in this case, NS is letter. This is the value that number of sample. So all the way how many points we need to know, we need to put in. Then we need to define earlier later. But this is just a basic idea. But this is what they call we want to assign a 0 value for this number lah. So let's say Q, so we want to assign all equals to 0. So meaning that if you have this is Q and T, so this is 0, all at 0. So in this case, we have 1, 2, 3, 4, 5, 6, 6 plus 1, 7. So meaning 7 lah, for example. So this is all the point that we define as a input. Right. So okay, another one is once we have this and then we override. So remember that I showed the cloud earlier in the slide. If you have first line, you create like this, and then when you reassign back, then you will override the value that you assigned earlier. So in this case, this is where we say that 5, and then the rest is equals to file and rest, right? File until n, file until 5. Because st is 5, 5 until n is equals to 1. So meaning that if let's say this is your 5, so the beginning part is still 0 because you don't override it, and then after that is overridden by the number. So meaning that it's not like this lah. Okay, because in the position calculation position, we cannot assign two value in the same position. For example, like this. Yeah. So you see there's a little bit a gradient. Why? Because you cannot assign one value at the same position at the same index. Right. Okay. So this is the input step that we need to supply. Let's say you have RAM, then you need to create your own RAM signal. So meaning that you know the value of Q, and then this is your T, then you need to assign something like this. Yeah. Let's say if you have RAM. Then how you get this function? Maybe y equals to mx plus c. For formula, then you can put inside here. Right. This is if you want to study the process dynamic according to the forcing input. So the rest is still the same, just like this for the process, and the solver a little bit different. If you look here, the ODE that I put in inside is based on the time frame. So meaning that a time frame from here to here, right? The time frame. right? So and then this is in this case dt, so dt, and then the h is ho, and then this is h new. So it will step by step, and then it will start again like this, it will start again like this, it will start again like this. So that's why we have a for loop. So if you look here, there's an indentation. So all this is inside the blocks, yeah, and then it will record the h. All right, so this is the this is not capital, this is I small, right? So I equals to, so at the moment at the first I, then you assign is as a 0, and then it start at 0. This is basically depends on your situation. All right, so depends on your this one lah. Okay. All right, so in this case, our my time frame for the simulation time is shortened by the segment. So then I will develop the process dynamic for the process, for the model. So if you look here at the one here, this is where we want to see the overall perspective. So that's why we use a 0 to 40, and then we put the value, right? Inside this time simulation time. Then we can just get something like this. Again, for the for this is much more flexible, so that we know that at certain point where is the location of the data or the output, and then we can see we can make arrangement of any custom sorry, this is not output, this is input, right? Okay, so this one. Okay. All right, so let's say you have you want to have custom input like this, then you need to make arrangement of your data point, and then from the data point it will translate into your output, then it will get the response according to your forcing input formulation. And then again, this is just to see whether you get the idea, they get the response or not. Then this is just plotting. So plotting in this case, if you look here, I'm using PLT. So previously I just used plot, yeah. So plot. So what does it mean? So here I already so this is black color. So from matplotlib, this is black color. So and then we have plot. So meaning that I don't need to do this PLT. So PLT meaning that I will just import matplot library dot pyplot as PLT. PLT, then I need to use plt.plot. So the calling is a different already because of the naming of the adding, how I add the library. Yeah. So it's just like this. Okay. So if you look here, the statement, this is the complete code. The complete code that I used to develop the previous exercise. Right, so if I call like matplotlib matplot as plot, and then I will just use this formula plot, and then I get the value. Right. So why I change many times here and there? It just for me it depends on the needs. In this case, I just want to to show to you all how there's a two way to call the library, not only import. Yeah, we can have this way from or import. Right. Okay, so this is what I discussed earlier. And then if you look here, I don't include this in the solver because this is not important for the process dynamic, but it's important in the syntax to run the program. Right. So this is just a definition for simulation time. I want to run from 40. Then this is my end of simulation, and then number of sample per graph. So in this case, when I generate a plot, how many points I want to have. So in this case, I just get 50. So meaning that the interval is divided by 40 divided by 50, then you get the interval lah. So more of this point, then will be your graph will be very smooth. Yeah, very smooth. I think this is just your numerical statement. So if you have more points, then your graph will be smoother, right? And then this is, I don't put this in the solver, right? I put in solver not? Yeah, I don't put in the solver because this is just to assign the value. All right, so this is a time to reach the time, and this is your simulation, and this is the sample. So from 0 to 40. So this is the time available, and then after that, you assign the interval. So in this case, 0 and 1. So this is what I mentioned earlier. So the interval here is dt. All right. And then in this case, this is the one that I discussed earlier. So earlier that I put like this arrangement, Q equals to numpy zeros, and then ST equals line by line. But in this case, I combine. So because of limitation of the space, but it still work in the Phyton, because the good thing in Phyton, you can do something like this. Q comma ST equals to this number, and then ST equals to 5. Yeah, so it's okay like this. Same like here. Okay, and then it's continue. When you run the process, you need to have a HP. So this one is to allocate, to store, temporary store. Create a temporary variable store. Why? Because we want to replicate, or we want to iterate this inside this for loop function, and then it will record HP, so that later we can plot at the end of the code. So this is just to store at a 0, and then after that they will override this value. Then this is not this is I, small I. Okay, and then equals to 0, and then as I said, this is the interval from previous and now. Previous and now, yeah, previous and now. So meaning that from previous 0, and then this is 1. This is 0, this is 1. Yeah. And then after that, this is assigned to D here, and then this one assigned to here. So meaning that HP naught, this is -1. So in Phyton, so in Phyton, -1 referring to end of the array. So meaning that, let's say H equals to 1, 2, 3, 4. All right, and then if you want to assign, if you want to call number 4, for example, then you can just use 0, 1, 2, 3. All right, so this is the number lah, 1, 0, 1, 2, 3. So this is, it will give you 4. Okay, that's another way. If because you don't know the position of your n, so meaning that the n is will increase, then the another way to call is just like -1. So -1 meaning that in MATLAB is just like n of the n, like this. So it will give you 4. So let's say after the iteration, you have h equals to 1, 2, 3, 4, 5. All right, so meaning that now you need to assign h. If you want to call 5, then you need to have now 0, 1, 2, 3, 4. So then you need 4. All right, and then another option is h, -1. But it's still the same. This is just technical issues, or you can just use like h equals I plus 1, for example. Yeah. So I is the end of the code, and then plus 1. So also can. Yeah. So like that lah. Or I, you use not I, in this case is uh, maybe I can. Yes, I. Then you can plus 1, then meaning that you position at every last. Okay, so I just use -1, so that is much more because it's very dedicated to the Python program. So this one is more general in any programming language. Okay, and then I just put figure. This one also one way. Let's say if you have many code, many plot. Let's say you want to plot figure 1, figure 2, right? So separate plot. then you need to assign the figures. Then Phyton knows that you create new figures, and then all the way you will assign the the subplot and according to the format. Okay. If you want to get more detail, you can go to apmonitor.com. I think you can get I get this I refer to this code lah for this access for this presentation. And for the workshop later in August, we use their product from AP Monitor. We get the hardware from, we have few hardware for the process, a small device to study the process dynamics. Oh, so that. All right. Okay. This is the process model. First one, right? So this is we call open loop. Process model, and again it's the same. If you want to go for a closed loop, the thing that you need to know, the first is the model, and then after that you need to run the simulation in the loop like this, and then you need to have several alternative, several operation, so that you can have a closed loop approach. Okay. All right. So those are the process model that I just very briefly. I believe if you want to talk about process model, we can drag so many days or so many courses, but it's just a very short. Just get you the idea, the surface idea, and then after that maybe you can try this, and then you can apply in your research or in your work. Yeah. All right. And then for control system, before we know that we want to design a controller, I think it suggests this. We can have many way to design or to check the stability. You can use root locus. We can use frequency in body, or we can use in S domain, Rouse array, all those things. Yeah. Okay, so now I just give you an example on Bode. All right, so I'm using Bode for this one. It's just a tools, Bode criteria. So I'm using sci-fi. All right, sci-fi, and then I'm using import Bode. So the keyword here is import Bode. So Bode is one of the function inside the sci-fi signal. And then after that, I will go for the closed loop system. Then I end the presentation today. Right. Okay, so for control system stability, so basically, let's say Bode is an open loop system. So basically, if you have closed loop, then you make it open loop, then you can use Bode also, or you can just disconnect your control system, then make it open loop. Yes, just I think this is uh, many expert here lah. I think no need that is right. So this is input, this is output. So this is we consider as open loop also, right? Okay. So this is just basic idea of how we can create a Bode diagram. So the most important is this. All right. So since I'm still using a transfer function approach, then I'm using this transfer function as I'm import the transfer function, and then I rename it as a TF so that I can manipulate TF object, and then after that import the body, so I can just use SB also, no problem. But since body is a good name for the start, then I'm no need to create assign to another value. Right, and then another one, I'm using import library, import. I'm using a matplot library, pyplot, and then I'm using something like this, right? Okay, so back to the question, or back to the exercise that we have learned earlier. So this is the transfer function, and then this is the numerator and denominator, and then we create a transfer function, a basic transfer function for first order. So first order system, I think we know that this is, if you want to see the corner frequency, I think if you learn this one, right? So this is the corner frequency like this lah. So this is 0.1, right? Corner frequency. Okay, so the most important in Bode, we need to know how to plot the Bode. So just like just now step. So now we use Bode, then we put it all the information inside here, the transfer function, and then we can call or we can create or we can have frequency information data, magnitude data, and then phase data. So all this for magnitude is in dB. Or if you want to use a normal or ratio, magnitude, then you can just need to convert to the negative to log 10, 20 dB, right? Then you can get the a value. All right, so terbalik. So this is dB, this is A, right? Or M. dB equals to 20 log 10 M. Right. Okay. So this is the this one. If you just use like this, then you get the dB, and this is degree, phase, and this is the magnitude, and then this is your frequency in radian per second. Right. And then how to plot? Just like since this is a semi-log, you can use a log also. No problem. As long you know what you do, log or semi-log. So in this case, I'm using a log. Semi-log x is a log, and then the y-axis is true, and then I put this is x value, this is y value for the first one, and then this is for second one. Right. So basically something like this. So once you run this code, then you will get this graph. Again, you need to have some this lah plot dot y label, x label to facilitate the additional features and the plotting grid. But this is just a essence of the code. I mean, you will get the graph. Okay, and then let's say you want to understand or you want to know the value, yeah, right? Because in the graph, it's just a graph. You can just say, let's say, oh, I want to know this one, 0.1, 0.2, for example, and then I want to know what is the value of here. This is what value, right? So then we can use compute certain. I'm using this function interpolate value first dimension interpolate. So in this case, I'm using. I want to compute AR, so I want to compute M here. I want to compute at the magnitude here, and then another one is this is not AR lah. This is M. AR is you need to divide by 1, right? 1 divided by that. Okay, so let's say I know my phase. I want to get the formula Fm is a function of theta. So I'm using the interpolation first dimension. So I put in the value for phase and magnitude. Then they will do the interpolation technique, so that you create a relationship between phase and magnitude. And then from here, I want to know at for negative 45, what will be my magnitude. So in this case, at 45 here, for example, at 45 degree, and then from here they oh, go up, and then I will know this M, right? So this is the first one. Go up, and then this is the way that how we think, yeah. Right. So this is the way. This is the code that uh, this is to convert the magnitude in magnitude. So in dB you get something like this, negative 3. So this is 10 power. In this case, 10 power. This is your magnitude in dB divided by 20. So the conversion from the dB to magnitude. Right. Okay. Right. Okay. So next. So now, if you want to use this stability to for the control system, so we move towards first we go for transfer function Laplace, and then we go for model, and then after that we go for stability. So then we need to if we have the stability criteria, then we know that we can design our controller, or we can perform a controller design or controller tuning. So in this case, this is the just I think just very I think there's many ways to do it. This is just one approach. I'm locating at negative 180, and then I go to the AR equals to 1, then I will see whether the system is stable or not stable. Or if you use a formula, then you can find your KU and PU, right? It depends on how you design, how you approach the case. Okay, so this is the just a very basic idea on how to find the stability point for at negative 180 at AR equals to 1. So in this case, I'm using this transfer function. So we have third order system. So definitely the phase is more than 180. Yeah. Okay. So in this case, how I translate this into the code in Python, then I will use this like this. So numerator is 1. So if you have 10, then you put 10 here, right? And then the numerator. So this is coefficient of the polynomial at the denominator part. So this is 1, 3, 6, and 2, right? So why I put 0, 0.0, this is not 0, it's just if you can assign into a float or integer. Yeah, it's the same. Yeah. Okay, and then this one transfer function I think we have discussed earlier. Then after that go to the body. So once you have the system, the transfer function for your for the system that you want to study, then you go for this one body system. Then you can get this information. Then you will get this is plot. So this is the idea of getting this plot. Yeah, getting this plot. So now the idea is now we want to apply the criteria of stability criteria. So meaning that at this one, for example, negative 180. So we want to know what is the value for magnitude, right? So if more than one, meaning that is a not stable. All right, and then less than one is stable. Right. So negative 180 go up, and then we go for like this, right? So this is the idea. So either way around is you need to look for this is like this, then you go for gain margin, right? Or another one is phase margin. Phase margin another way around lah. You start from the magnitude, then go to the phase, and then you get the phase margin. So in this case, I'm using the gain margin approach. I think I just give you idea, but the later the details I think you can just refer to any textbook, because the idea of Phyton is just tools to get you the value. Yeah, just like a calculator. So to calculate the value. Yeah, to calculate the value. Okay. So in this case, now I want to apply this information to study the stability. So first step, I want to check at negative 180 what is my frequency, right? So in this case, from here, I want to know this value. So how I do it? So this one. So WCR, all right, and then WI. So this is the frequency at negative 180. So how I get this? So it's just like the one that I described earlier. So I'm using the interpolate first dimension, and then I can assign this at negative 180. Then I can get the frequency. Yeah. Okay. Later I will show you the complete code. Right. So and then after that, this is a semi-plot, semi-log for this one. So 0.0 at this point. This is just the line, the red line. So this is not important. But if you want to share the straight line, then this is the one lah. Okay. And then after that, you display the text according to the statement here. Yeah. So then you can display the text. So basically, once you run, the idea is to run this code. You get this value, WCR. So this is the WCR. Okay. So once you have this number, then you need to put at here, right? And then you know this value. Then you want to go here, and then you want to find this. Yes. This is the idea of the idea for the gain margin. Okay, right. Second one. So once this is a settle, now we go for second step. So we want to find the magnitude at W equals to the WCR 2.45 at this point, and then at this point we want, this is what this point we know from the earlier calculation. Then this one, the most important is this one, magnitude I WCR, and then this is magnitude sorry, so this one, okay, and this one, right? Only two. So this is your X, this is your Y. So magnitude I WCR is the same, right? Oh, sorry. So okay, all right, so this one, yes, the same. So you want to find magnitude. Magnitude is a function of W, like this. So this is this is the formula that you need to know. Same like earlier. So this is the formula, or this is the code that you need to know to find uh, W function of phase, like this. Okay. So once you know this, then you get the value for the magnitude. Like this is in the decimal point. Then convert it to magnitude. Okay, and then convert it to like this, and then after that I will get the AR. So if I want to know the margin, then I will just divide by 1 divide by AR, 1 divide by AR, then I can get the margin, gain margin. Yeah, gain margin. So then I know that this is the gain margin, that in this case gain margin is 16.2. Okay, right. So gain margin 16.2. What does it mean? So system is stable or not stable, right? Okay, system is stable, not stable. So you have a gain margin, right? So it's stable lah. So at the bottom, gain margin. Okay, not stable. Your margin at the top, right? Above 1. Okay, right. Okay. So this is the complete code that I run for the exercise earlier. Okay. So the different that from the code is this one, correlation. This one. Right. Okay. So this is the interpolate from phase to magnitude. So what does it mean? So magnitude is a function of phase. All right. So and then phase, sorry, frequency is a function of this one is a function of phase. And then in this case, magnitude is a function of uh, frequency. So this is where you, let's say this is where you find the correlation, so that I can apply in the exercise at this one, and at this one. All right. So the rest is not is still the same that I discussed earlier. So this is the graphical just for the eye view purposes. Basically this is not necessary. I mean if you want to get the controller design, then you can just use KU here. Then you can get the KU over AR equals to GM. Then you can find your KU, right? And then you can use PU equals to PU is a function of W C naught, right? Then you can get the controller for Ziegler-Nichols already. Yeah. So that's the how you design the controller. Okay. If you proceed after the frequency, after the what do you call? After the stability analysis. All right. So this is just to show in the graph nicely, so that you can present in your report. So I use this form code if you want to learn more on this in this code. Yeah. So I make it simple. In this code, they mention many things. I did some summary on that. Okay. So the last point for today, a control loop control system. uh, Closed loop system. So this is a negative feedback control system. This is a most complete complete block diagram. So basically, process and controller is the most critical part. But if you have final control element, measuring element, just adding the process or adding the transfer function accordingly. At the end of the day, we want to see this. Yes, whether if you have a set point, whether the control system are able to bring to the set point. All right. So just the same like this. Okay. All right. So a process variable, set point, and then in this case we will have O as our output, control output. Okay. So we use SP, OP, and then PV. All right. So in this case, I just use a process something like this, a most generic one. So TP, tau P, tau process TP, yes, and then KP, and then this is U input to the process U, and then Y is the state here lah, Y. Yeah, okay. So this is the process that I will use, and I'm declaring a process something like this. Okay, and then this is define, and then I'm defining the process in terms of, if you look here, Y and T is the most. It's a maze, it's mass, and then afterwards it's just a afterward, this is just a args, additional argument to the process, to the function lah, to this process. Okay, and then it will reply like this. So let's say if you have more transfer function or more equation ODE, then you just add accordingly. Do it, put in inside this accordingly lah. Okay. Let's say your process is very complicated, many ODE. Let's say last time we have polymerization. We have most like 50 ODE inside the model. Then we will just add it all inside here. And Y, just a single Y, but we have 1, 0, 1, 2 until 50. Yeah, Y. So meaning that like this lah. Okay, so it depends on your model, depends on your research, or depends on your case. Is like this. So this is just very basic idea of how you can use this for to study the control system or closed loop or controller performance. Yeah. Okay. So in this case, and then I will use a solver. So meaning that you need to run the code inside. Make sure that it will start the looping until n, from 0 to n. Yeah, so simulation time n, and then in this case I will just use a for. I mean this is the the highlighted code that I that important in this case, right? So in this case, if you look here, you start with the error. So all right, so this is we'll put in here. So this is SP. So SP, we know that our SP is just like the one that we used earlier in the queue. For example, like this, right? Okay, how you get the SP is based on this. You need to create a data points for the SP, and then PV. So PV is according to the after the first iteration. So then the PVI, I meaning this is the first one, I, and then after that it will, so I at 1, then there's a initial value problem. Right, and then after that you assign your PID value, PID according to this information. All right, so KC tau I and KC tau D is just like U equals to, in this case is K E plus KC over tau I, and then this is the integration of E dt plus KC tau D dE dt. Yeah, because of the dE dt, dPV, right? Okay. And then after that, they will compute the value of U. So in this case, is OP. Yeah, OP. All right. So this is the controller part. So basically, this is the incoming from the controller input. So this is the controller part. And then once you know this value, then you put it inside the ODE to solve the model that we discussed earlier. So if you look here, so this is process, this is the process, and then the initial value is starting from the point of the simulation, right? So it's starting from here, and then it will start at this one because we use a delta, and then we'll move to second point, and then move to second point like this, and then move to second point. So it's the same like the one that I discussed earlier in the process dynamics, right? And then after that, this is just an argument, that additional argument that you put in inside the process, or you can just put in directly inside the process. No need to have a additional argument also. So depends on how you this one. So for KP and tau, but for OP is must you need to put the argument so that the information, the signal can pass through the process block. And then you update the value for the PV, then it will repeat again until end, simulation end. Yeah. Okay. So this is the running ideas on the process part. So this is on the process part. Process block. This is a controller block. Right, this one. So this is process block. This is a controller block. Okay, and then you will repeat until end the simulation, and then after that you will run you see the plot or the result, and then you will get like this. So this is just make sure that the graph is visible lah. Make sure it's like very thick line lah. So normally by default is 1. So if you want to get more, then you get 20, then you get very big, then I think it's ugly graph lah. Okay, so in this case, just a legend, just to show the ideas, the label like this, yeah. And this is the all the code that all the code that available for you to do, or for you to uh, to use. So in this case, I'm using NumPy, Matplot library, and SciPy, and then this is the model that I developed that we use. Okay, and then this is NS, as I said, this is number of sample. So along the line, so your line like this, so you want to have 300 points, right, from 0 to n. So from 0 to n, you need to have 300 points. This is you basically more points better, but you will increase your computational time. Yeah. And then in this case, lean space ns divided by 10. So in this case, I'm using 30 from 0 to 30. Yeah. So from 0 to 30 points. So meaning that 1 point is 10 data. So from 0 to 1 unit time, you have 10 points. Okay. Right. And then this is the delta is the same like the one I discussed earlier. So like this. So this is time 0. This is time 1. Right. So you get the delta. So and then after that, this is just storing properties, so that it just like the earlier that I mentioned in the H. So it's just a temporary store. Then after that, they will override after it go to the loop. Yeah. And then this is the declaration. So declare for the KP, KC, tau, and tau D. And then this is the value that tuning that say you have value 2, and then this is right. So this is just data that later, if you, let's say you want to make sure that the response is a fast response or sluggish response, then you can just tune from here lah, and then you can just assign the value accordingly. Okay. uh this is you need to set the limits. Maybe good to have a limit. And then in this case, this is the loop through times. This is where the main simulation. This is where the simulation about. So this is where the simulation. So I just point out the information for this one. All right, and then after that, the PID. the controller block. Okay, and then the last one. Okay, but here is this is just a limit so that you don't after the OP. Sorry, this is the controller, and then you have a saturator. So that minimum is 0, maximum is 10. So that your system will not go above 10 and 0, right? So this is the option lah. I think this is the option. This is this one lah. If you have, then it's good. If you don't have, then you need to you need to make sure that they will not or exceed certain limit. Then you will get your error failure at your code. Okay, and then this one is after this. Okay, and then this is where you reassign again your value, right? So reassign again like this, continuation from PV, and then reassign back, and before they go back to the same loop. Okay, and then the last part, this is go to 4. Okay, and then the last part is a process, just display the value. So in this case, you display according to the set point, process value, and then you get the idea. Right. Okay. All right. So that's all from me at the presentation. So you get graph something like this lah. After you run the code, then you graph something like this. It's black as a set point, blue as the process variable. All right. Okay.